I really enjoyed putting the previous recording online. I expected it would be much harder. Seeing it was 2 hours and 23 minutes long. But I learned how to do the timestamp stuff. So that was pretty cool. I didn't know it was that easy. So, the next thing I want to learn to do is this background here. I want to do what Anton Petrov does and be able to change it as I'm talking about stuff, because that's a powerful tool. I want to show you something that I caught off the web. So here we are now. It's a month since the James Webb Telescope started to bring us the images that show galaxies, and again, yet to be peer-reviewed by a bunch of Big Bang cosmologists. So, don't be disappointed if the papers get turned down. But basically, the observation that there are fully fledged galaxies with second generation stars inside what used to be the Dark Ages preceding the Big Bang. Then the Dark Ages to the Big Bang is very important, because think of the Big Bang as being a brick wall, and you're driving a car at 60 miles an hour towards this brick wall. There comes a point when you cross a line where no matter how hard you step on the brakes, you're going to hit that brick wall. And for the Big Bang, it's hit that brick wall because of galaxies that are only 180 million years old. You can't create a full-fledged spiral galaxy with second generation stars in 180 million years. It takes our galaxy 200 million years to do one rotation. So, how do you make a galaxy like that? It just doesn't match. And I think that the people who are challenging the Big Bang edifice need to hone in on this like a laser and keep, this is the eye on the prize moment. You got to look at this. So let me show you some of the things that are strange and occurring. So let me get this. This is Anton Petrov taking the knee for the I wonder if I can, I guess I have to be my desktop screen too. Okay. All right, guys, take a moment here. Grab that. So here's Anton Petrov. Who's done this thing called "Did James Webb Prove Big Bang Theory Wrong?" And he goes into this whole thing about the Big Bang not being wrong. Here's the priest, who came up with the Big Bang theory. Of course, Catholic Church loved that in the beginning, as the Bible says. And then he goes through all the whole gambit from A to B of what makes the Big Bang seem to be, love this one. Seem to be, there's the Dark Ages. Hey, let's talk about the Dark Ages in here. It's the Dark Ages. See right there. Oh no, we're not going to talk about that. So here's the end of this thing here. Let me play this, and I'll go to about here. Hang on a second. Sound. I'm not getting sound.
The evolution of early galaxies. The initial evolution of some of these early galaxies did not progress as the scientists originally predicted. It looks like the galaxies were able to form much earlier, developing into larger structures and into more cohesive structures with more success than some of the early simulations predicted. And that's of course what the scientists are currently questioning. They're basically questioning some of these simulations we have and some of the early predictions about how early galaxies formed. Something here doesn't match. Everything else though matches exactly. And so the Big Bang Theory is not questioned by anyone that does these studies.
Your audio is off now.
Did you guys hear that okay?
Yeah, that was fine. That was fine.
Yeah, did you hear that last part? He says that something here doesn't match, but the rest of it matches perfectly. I mean, it's kind of like saying
wrong, right? But if you're talking about the cosmic background radiation and the smoothness and all the other factors, and of course the always recurring redshift and how far something is away from everything else, all of that is fundamentally fine still, right? That still matches with the Big Bang Theory. That still matches with everything that those models assumed. What doesn't fit is the growth and the progression, so the cosmogenesis and the creation and formation of these galaxies. That does not fit. So those you can easily, well, at least they can easily detach, call it the cosmogenesis, the evolution of the cosmos from the actual evolution of time and space, right? That's allowed because they just say that, well, those things we don't understand perfectly in detail yet, and stars and things, how they exactly pull together, and how stars are created and how galaxies are created. Well, we can look at those variables and we will fit them later. So it's just decoupling evolution from geology, right? It's the same thing.
Yeah, I mean, for me, when I look at that, it's kind of like saying, yeah, we have this perfect working clock, except one of the cogs isn't functioning. And so what is the ultimate outcome of this is really that the clock has stopped, and for the Big Bang, yeah, they can move the goalposts further back. First of all, I mean, the 3.7 billion years is kind of like a stopwatch set piece, because that's what the redshift is telling them. Well, if that's what they're relying on, and they're coming to this point called the Big Bang, which occurs 180 million years before fully fledged galaxies, you've got yourself a real problem. Now, okay, move the goalposts further into the event horizon. Sure, you can do that. Now, JPL conveniently won't be able to look at galaxies that far in, but at that point here, you've demoted what is a theory, the Big Bang Theory, into a hypothesis. And worse still, probably a hypothesis that's more faith than it is actually a scientific statement. So I think even at its best, it's in deep trouble. How this is going to evolve, I think the first thing that's going to happen is those papers that I think it's 3 teams. I know of 2, I've heard 3 teams that are looking at these distant galaxies. You remember, they're going to go before a peer review board that is almost exclusively Big Bang theology. And are they going to pass muster? Maybe yes. Maybe they'll have to modify it and say, who knows? But I think there's a very strong possibility that the only place they'll actually be able to publish unedited will be on electric journals, and that are not seen by the professional cosmologists, because it's an embarrassment. Will this last? Will this keep up? No, I don't think so. It will gradually erode the Big Bang hypothesis, but it's going to take time. There's too many people who have too much investment in the Big Bang formula. They have written books on it. They have done everything they can. And I see that Chris Sellye has sent us a link. Let me see if it has something we can go and look at. Okay.
The Big Bang, a theory that proposes that everything.
Okay, I'm going to stop it for a second, and I'm going to run it on the screen, Chris. Hang on. Share screen. This, of course, takes time and effort. Stick it on screen 2. Expand it. And begin it from beginning. And let me, guys, let me know if you can't hear it or something. Just give me a shout.
The Big Bang, a theory that proposes that everything, everywhere, all at once comes to life. The limitation of that theory is that everything and everywhere prior to the Big Bang is difficult to comprehend. The Big Bang theory is the best model we now have for the genesis of our universe. Astrophysicists have demonstrated that the hypothesis adequately describes phenomena observed in space over decades, such as persistent background radiation and elemental abundances. It's a solid framework that provides us with a good picture of how the universe came to be 13.8 billion years ago. But in previous research, a team of theoretical physicists claimed to have identified traces of prior universes hidden inside the leftover radiation of the Big Bang. Our universe contains a massive collection of observable stuff, including gas, dust, and stars, as well as unexplained dark matter and dark energy. In some ways, this cosmos is all we know, and even so, we can only study roughly 5% of it directly, leaving the remaining 95% a mystery that scientists are actively striving to unravel. However, one group of scientists claims that our universe is not unique. Rather, it is one of many universes that are created, expand, and die. In a recent study that has yet undergone peer review, using the James Webb Space Telescope's recent data, a galaxy dubbed Sears 1749 was discovered roughly 220 million years after the Big Bang. At that age, galaxies should not have developed so quickly. CCC, as it is known in nerdy physics circles, is a theory proposed by theoretical physicists Roger Penrose and Vi Gerzadian that states that the cosmos goes through endless cycles. Each cycle starts with an event, such as the Big Bang. Our universe was filled with a thick, hot soup of plasma when it was extremely young, before any identifiable components like stars, planets, or galaxies formed. As the cosmos cooled, particles could finally join to create atoms. The interaction and fusing of these atoms eventually resulted in all the stuff that we see today. However, we may still see remnants of radiation from that early, dense era in history of our universe. This remnant glow, known as the cosmic microwave background, or CMB, is the earliest form of electromagnetic radiation and fills the whole cosmos. If the CCC hypothesis were correct, the CMB of our universe would contain indications of prior universes. CCC theory claims that at the end of a universe, when those final black holes evaporate, they should leave behind a signature that will survive the death of that universe and endure it into the next. Detecting such a signal would be substantial evidence in favor of the CCC theory. However, it would not be definite proof of past universes. Cosmologists confront a severe challenge in their hunt for these Hawking points, since the CMB is feeble and changes unpredictably. On the other hand, Penrose claims that a comparison of a model CMB with Hawking points and actual data from our CMB has demonstrated that Hawking points exist. If correct, this would be the first time evidence from another universe has been discovered. Science is about making little steps forward in our understanding, forming progressively solid conclusions based on observations. The findings of astrophysicists and cosmologists over the decades are consistent with the Big Bang idea. If we apply Lerner's alternative explanation, they don't match up nearly as nicely. That is not to say that scientists will not unearth evidence that contradicts the Big Bang idea. They could very well. But, for the time being, it is our best explanation for describing what
Well,
Yeah.
I still end
Yeah.
up
Go ahead,
going back.
Jakob.
I keep going back to the problem with all of these things is that it's assumption upon assumption upon assumption, and I honestly believe that it goes way back to the first assumption. I know I like to speak in allegory because it makes things a little bit easier to understand, and I like to compare the assumptions of a fixed speed of light with a fixed speed of sound. Again, if you were on the planet Earth and you were doing scientific measurements, right? And you assumed, based on your little laboratory model, that the speed of sound is 330 meters per second, whatever, something like that, right? In these conditions. And then you were measuring, well, basically, you were like a bat. You were using sonar and you were looking through the fucking air, right? And let's say that on this sunny side of the Earth, right, the average temperature is 21 degrees, just like in my experiment. But not every location is going to be the same. But even then, you might actually even it out. So I could send my sound to you, Stephen, X amount of kilometers away, and it would move through a cold patch and then a hot patch, but the average is the same. Now I will have a number and a distance based on my assumption in theory. But if I would remake that experiment at night, I would get a completely different result because of the change of ambient temperature. I know this gets a little bit tricky, but the point is the same. If you are assuming that the speed of light is the same all the time in a vacuum, in all of the universe, right? Then everything will give you this Big Bang model. But I will like to claim, if you start considering that the speed of light is actually sensitive to the nature of the background vacuum, so the empty space, the non-matter part of space, then depending on what maturity of the cosmogenic universe you're moving through, whether you're moving through a tendril of galaxies, or whether you're moving through one of the big voids, the speed of light is going to be different locally. Yeah. Now you have the situation where then when you look out, what you're actually seeing is not an expanding universe per se. What you're seeing and the redshift and the background is actually call it a net curvature of space. You're basically seeing a result that is like an optical illusion, because the maturation of space happens at a set speed and direction where it basically differentiates from nothing to material something, right? So what you are actually getting is you're still getting slightly the same average, so you can almost conclude it, but because of the age of the universe and how long your close environment has been changing, you're actually seeing the change of space. So our curvature of 14 billion years, that limit, that horizon, is actually the result of the maturation nature and the maturation speed of space. How fast things can go from uniform nothing to actual now.
From a more brutish point of view, well, let me just address that video we just saw by, which sort of talks about Penrose, what I call oscillating universe. Yeah, it's kind of interesting, I noticed it was from 2018, and it doesn't, it addresses the cosmic background. How about this for a cosmic background? One of the things about space is, if you go out into intergalactic space and you grab a cubic centimeter of intergalactic space, I couldn't tell you what period of time it would be, but a hydrogen atom will pass through that cubic centimeter within enough time to where you could probably go and get a cup of coffee and come back. A hydrogen atom will have passed through that cubic centimeter. Now, if you've ever been by the beach and you've put your head under the water, as waves come in, you hear this sort of clinking, tinkling sound. Well, think of these atoms, these hydrogen atoms, occasionally, once in a blue moon, colliding with one another at very high speeds. And as they do that, they let out a spectral signature. And that spectral signature is red. It's in the red end of the spectrum. That's hydrogen. And as you go back further, not back in time, I hate to use that, but if you go further away, you see the shift in that little tinkle that's occurring. And as you go further back, it turns into this red fog that the Big Bang is called the Big Bang, but I don't think it's a Big Bang. I think it's an event horizon. The way I like to describe it is you know, you've got a crystal on your thumb. That's your this is our galaxy. Around you is a sort of a frozen, gentle snow of galaxies. If you go 24 meters away from that, in any direction you go, you get to that red fog that you couldn't penetrate. Now, of course, you're standing in another location. The red fog is elsewhere because that's what fogs are like. But it's uniform. You ever been in a London fog? You know, it doesn't come in clumps. You know, it's like, it's uniform. And you, as you walk through it, you can see 3 or 4 feet ahead of you. And then what's behind you is gone. You know, it's like, and that's how I think the universe it probably, that's the phenomenon of the redshift is really walking into a red fog, and that's the event horizon. I think that's what we're looking at, and that interpretation is, you know, I've not seen it anywhere. I'd like to see someone challenge that idea. Again, this is not my, you know, I don't have a horse in this race. What I love about this is the factual, the visual observations of the galaxies that we see this far away, turning out to be just like galaxies around here. And that, to me, that piques my curiosity and makes me want to see how Big Bang cosmology is going to deal with that.
Well, I don't think it's going to deal with that because they don't have to. Again, this is back to, from my point of view, in our stellar cavity with our little sun and our 9 planets, 8 if you want to be specific. But the point is, we are like flying through space in a little yellow submarine, right? And we're looking out a lot like a sonar specialist would look through the waters, right? But if we're basing it on the wrong assumptions, if our computer is calibrated wrong, you're not going to see the right things. You're going to mistake a big lava drive submarine for a big mammal, because your software is wrong and they sound slightly similar. Again, if we keep making the same wrong assumptions, we're not getting facts and reality. But what I'm saying is, it doesn't matter because it has no utility. It doesn't matter whether it's the Big Bang or not the Big Bang. All these models are arbitrary. It's just, it fits very well and very comfortably with the engineering mind and the theologian mind. They love the fact that something starts and you can say, Bereshit bara, and then God made light and there's a universe, right? That's pretty much what they want. It's simple, it fits, and it works until you can find reason and utility to change your mind.
And you would not say that the discovery of galaxies in the dark ages is kind of like a bit of a problem?
No, it is not a problem at all. No
Because
one on planet Earth needs to care about this, because it doesn't change anything for us. It doesn't help us move into a different direction. It doesn't give you better tools. It doesn't give you better technology. It doesn't give you better living standards. It doesn't help mankind at all. It doesn't matter whether the universe was created by a big cow that was killed by Aesir gods, or whether it was the churning of the Milky Sea, or whether it was God just said light. It doesn't matter.
Or turtles on top of turtles.
Exactly. It does not matter. It has no practical
application. Are you then saying that we can just happily go along with whatever model we like?
Yeah, because this is just like, you know, when humans like to see images and patterns and shapes and everything. Well, when you and I lie on a beach and we look at the clouds, and I say that looks like a bunny, and you say no, it looks like a dog, doesn't matter. It
Yeah, no, I
really
don't go.
doesn't matter.
I'm sorry, I don't see it that way at all, and I think that the proof of that is with the opening of the door with Johannes Kepler and Tycho Brahe, and suddenly the universe, it becomes something that we can actually wrap our heads around. I think that's important. And I don't think that our technologies and our engineering skills and everything that has sort of come seems, if you draw an technology line, you come to Johannes Kepler and Tycho Brahe, and suddenly everything takes off at that period of time. There's the printing press, and the idea of something that's been fixed and solid for 2,200 years, the geocentric system, was really the sort of foundation that made us solidified into a very sort of things are, it's spaghetti, it's the spaghetti universe, it's the cow universe, there's turtles on top of turtles, no one gave a shit. But I don't think that's the case anymore. I think people, and I don't just mean cosmologists, I think that a lot of people are really curious, want to know how it functions, and there are the tools that show us how it functions. The latest one being the James Webb Telescope, that's looking at these galaxies that are there. Now, you could say they're not there, that is a figment of the imagination, or, like your religion forbids you to believe that they're there. But from a purely observational evidence point of view, I'll ride along with the objective, that imprecise tool, objectivism, that we need to have.
Love. Okay, you're a philosopher. You're in love with the ideas and with the academic purpose of lying on beaches and looking at clouds. In the real world, this is an Antikythera device, right? You can travel around all of the Aegean Sea with your Antikythera device and say, look what I made. It's amazing. It can precisely predict all of these wandering bodies in the sky. And it's like, and everywhere you go, the reply will be the same. What is it for? What can I use that for?
The premise of it was false. I mean, one of the things we were talking about earlier, Jakob and myself, was that Antikythera device has to include the epicycles of the planets. Without those, and if it had been made after Johannes Kepler and Tycho Brahe, you could remove 10 of those wheels. I mean, it was made an overly complicated, mathematically eloquent system, which was describing a universe that didn't exist. And I think that to a large degree, that's what we have in the Big Bang. We have huge assumptions about what redshift is. And we've basically built and we build these mathematical models with the formula of gravity, largely ignoring the electromagnetic plasma configurations and how they pervade space on a galactic level. This is sort of like swept under the carpet, and we can't go on like this. I hate the schism between the electromagnetic school of thought and the gravitational school of thought. It does a disservice, and it basically solidifies the fact that they both exist as opposite schools, solidifies this sort of like ingrained, stupid inflexibility that we have today, where the big bangers, someone like Alton Hart comes along, and it's not like you're welcomed into the fold. You've discovered something new. It's like you're iced out of what's being discovered because it doesn't fit in the groupthink of your system. That's deadly. That's deadly. That throws us into another dark age that could last for another 2,000 years, where we entirely do not understand even our local, when I say our local universe, I mean from here to 13.7 billion years ago. I mean, it's a hindrance, and it's a deadly hindrance.
And again, I'm going to be the devil's advocate here, because it's not that I don't agree with you. I academically and philosophically, I completely agree with you. But the problem is that I would like to just ask you, so you're talking about gravity and you're talking about electricity, and I'm just going to ask the very simple question that the world will ask. Will it give me anti-gravity devices? And will it give me room temperature superconductors? If not, I don't care.
Now,
I really don't.
you can't say that because, I mean, that's with Johannes. If you had asked those questions about Johannes Kepler and Tycho Brahe, they would be stumped. They wouldn't be able to say, no, this is going to open the door to an entirely different way of viewing the universe, and it's going to lead to things like, we can make things because of what they discovered that have utilitarian uses in everyday objects. And will the fact that the Big Bang may have to change and we might have to see things differently because now we understand more, will that open doors of, as you say, anti-gravity or more gravity, the gravitational induction? Yes, absolutely.
And then it's back to, and again, I am being the devil's advocate, because this is why people have been throwing so much money at a completely bogus dream of fusion, right? They've been throwing money at tokamaks for almost 40, maybe 50 years now, right? Because the dream is there that we will get near free energy. The fact that it's theoretically ridiculous to try and create a fusion reaction based on a torus-shaped filament that's compressed to maybe produce fusion. It's just it's silly, but it carries the dream. That's why people throw money at it. And again, you need to come up with a similar prospect to the tokamak guys that will give us something like anti-gravity, super-sized airplanes, or solid state superconductors that work at room temperature, so I can multiply the efficiency of my computer by 1,000%. If you do not tell me why this is useful, you are basically doing the equivalent of what is fundamentally basic science. Just keep trying and see what happens. You could say that going to the moon from a utilitarian point of view really had no value, but it brought along a lot of technology. So you have to put that in your sales pitch, because right now, cosmology-wise, what happened 10 plus billion years ago doesn't really matter to anyone on planet Earth. It matters to the philosophers. It matters to the long perspective thinking of what is humanity and what is the nature of the universe and all of that, of course, but it does not matter to most people. It's again back to the, if you do not have airplanes and massive ballistic missiles and cannons and stuff like that, I don't care about whether we're using a Aristotelian gravity model or a Newtonian one. It doesn't matter. It's only when it becomes utilitarian-wise valuable that Newton matters, because if you want to build anything bigger than cathedrals and towers and pyramids and all that shenanigans, if you want to build anything more complex and bigger than that, you need structural engineering science that is based on actual measurable numbers, right? That's when you need Newton, because then you can predict all these things before you start building. But before that, you didn't need it. You had tradition. You knew what an arc would do. You knew how much carry load it had. Pretty much, you had rules of thumb, all that stuff that craftsmen would have. You didn't need it.
Let me go back to the first part of your commentary, the tokamak reactor and the dream of a controlled nuclear fusion. I believe that controlled nuclear fusion is possible. I don't believe they're going to do it with the lack of knowledge that they have. I don't believe they've put the time in to understand the experiments necessary to understand the nature of plasma. That's something that they discovered very early on. I mean, their first tokamak reactors were treating plasma as a hot gas, and applying the laws of gases to it. And it's only by about 1965 that they're starting to realize that, there's this little problem that's occurring. It's called, plasma behavior. And at this point here, what we should have done as a society is produce hundreds of laboratories experimenting with plasma behavior. We didn't do that. What we did was we let the engineers just keep doggedly doing the same thing on larger scales, and realizing to their horror that plasma behavior was scalable too. And then the latest trick that they're trying to do is to, when these turbulences occur, to have a computer correct these turbulences that are occurring. Hey, why not do the real scientific thing and figure out on a smaller scale in different laboratories all over the world how plasma behaves? So that's the first thing I wanted to mention. The second part of your commentary made me think of geology. Who cares about the layers of geology going down? How is that going to build me a better toaster and all that? But what the layering of geology did was it sort of gave a foundation, a very firm foundation for Darwin, and being able to say, look, this goes back in time. It gives us, it takes us away from faith and puts us in the driver's seat of fate, that now we are in control. We're the ones who made God, not the other way around. And it's a profound moment. And we still struggle with this today. I mean, there are areas in the United States that are like in sort of the brutals, are fighting tooth and nail against these obvious scientific facts that are sitting there. And as you say, what does it matter to me? It's a slow, very hard process that mankind is having to go through to realize that that the fate is in your hands. It's not, no one is coming down to save you. There's no mysterious force out there that's going to make everything good for you. And it's hard. It's really hard. And it's taking us centuries to be able to come to terms with that.
But again, I'd like to point out that you're correct that after the fact, when discovery has been made, a lot of practical applications and values are then created eventually. But those cannot be predicted. You can't predict which type of new discovery will give what type of value for society. This is why everything, when you're looking at scientific progress, has been, at least I would say 90% of it is necessity is the mother of invention. Like when we discovered the things like subduction and geology and all that, well, we basically discovered that because someone was trying to pull cables across the Atlantic and all these things. It was because there was projects that had an actual application value, so you needed the other stuff, and then eureka, something was found, right, and discovered. How long did it take from the invention of or discovery of electricity and electromagnetism until you had things like radar and actual electric light? It took hundreds of years. We didn't get proper radar until there was planes trying to kill people in England, right? So it's always about utility. It's always about practical application. So science need to be a little bit more of a salesman and explain, well, what is the value of basic science? What can come on the other side? And what is the immediate utility of this new direction of research and science? And of course, when you're talking about things like fusion, the argument is strong, because it's a lot more likely that if we did something like split up these things and did tons of plasma experiments, and everyone had a Farnsworth fuser, and everyone was playing with polywells, and everyone was looking at weird behaviors of interaction of plasma, maybe we would get some information that could be published, and we could actually get a real fusion reactor that would work, right? And I do think that that is eventually going to happen, because my strong suspicion is that a lot of this has been shelved because of international geopolitics and personal interests. And I know that people will say, oh, you're just a tinfoil hatter. Well, maybe you should go and read up on who killed the electric car, and maybe you should read up on the infinite fucking light bulb, because these things are not just tinfoil. These things are facts.
Yeah, I want to segue for a moment to Chris, who brought up am I pronouncing it Robitaille? Robitaille, he's got a, for those of you who haven't got to watch this, definitely go and watch. He's kind of like the ultimate heretic when it comes to universe interpretation. He's very good. I have a lot of respect for him. I called him out on one thing, because of my interest in the sun, and that was he didn't know, and I hope he corrected it, but he didn't know that the sun does not have an oblateness in its rotation. That was discovered in 2012, and he didn't know that, so it was kind of like, that's
too round, is what you're saying.
Yeah, but a lot of what he talks about, you may disagree with him, and you may be a follower of whatever model is presently, the accepted model, but he gives you food for thought. There's no question about it. There was a sort of a counter YouTube site that was supposed to naysay a lot of his stuff, and it was just laughable. This attempt to sort of derail him as an imposter and someone who's just sort of taking advantage of people, and you see this kind of stuff a lot.
He makes premature leaps. It's a lot of his things are very interesting, and I think he might actually be very much onto something, but he makes these premature leaps based on his then assumptions, and then he basically ends up stacking up his own amount of premature, potentially wrong assumptions that people can then shoot down because there is no proof for them.
Yeah,
right?
Yeah, and
so he's got exactly the same problem as a heretic. He's valuable, but he makes the same mistakes. This is, again, I go back to Velkovski and the whole thing of talking about punctuated equilibrium and development in catastrophic leaps, right? He has been proven right, but when you listen to the man back when he was saying these things, he sounded like a nutter. And he was a nutter. He made way too many leaps. He predicted things that was completely out left field and didn't make any sense, and was easily disprovable. But he did change the behavior and the attitude of the scientific community, where they kind of accepted his premise, which is, this is not a linear, gradual development. It is always in punctuated equilibrium and leaps and phase changes and things like that. And it's very much the same type of thing that we need to start inducing and pushing into the current cosmology's point of view, because they are doing exactly the same, with always talking about these nice curves and gradients, and everything progresses nice and neat and according to a clock. Nothing else in the universe seems to do that. Why do we assume that it does that on that scale? It's just flawed, in my opinion.
What I find sort of mildly disturbing, and it's not Robitaille's fault, but this sort of this, and it seems to be just increasing, this need of a lot of people to glom onto and become groupthink guardians for that, for a given individual and their belief systems. And I mean, you do definitely see that with the Big Bang on a huge level. Possibly what makes the Big Bang so profoundly attractive to so many people is the three first words of the Bible, in the beginning. This sort of deep need we have to know that there's something started and something ends. The idea of something being infinite it's so revolting to the human mind, and so hard. Of course, it's almost ungraspable. It is ungraspable to think of something that is forever and ever. Amen. I wish the Bible would have sort of pushed that to the foreground instead of in the beginning.
It suffers the same as all faith, right? It suffers the problem that all of these armchair heretics wants to be a prophet. It's very ego driven. They want to be the new prophet and they want to have the new religion. That means that it's no longer based in facts. It's no longer based in objective progression of science. It's just about stealing hats and seats and dethroning each other. And that's where I get frustrated, because you can see it, how they tilt and then they become estranged and become fringe and pushed all the way out to the edge, and then they start their own little cult and their own little followers, and now they are misunderstood prophets and martyrs, right? Then we won't come to any agreement. We won't actually discover anything new if everything is so ego driven. It is a fact that all of the established science that we're using today has proven its worth, has proven that this is massively valuable. So you can't dethrone Einstein. What he did to our science is massive. What Newton did is massive. What Darwin did is massive. But if you want to try and supplant these people with your new little god, I don't mind whether it's Helton Arp or Alphine or whatever, and you want to have everything be about conductors and electricity and whatnot, whatever. The point is, if you are trying to dethrone someone, if you're trying to ridicule some branch of science today, you're not really a scientist.
Yeah, no, I agree with that. I mean, you go back to Newton, Newton's laws are just fabulous. They're basically anything you want to do with gravity on a day-to-day basis, Newton works fine. You throw time into it, and Einstein, and there you have, and that's mind blowing. I mean, but anybody who's like casting Einstein aside is kind of like, oh man, come on, man, be a little bit more humble about this.
But if you put Einstein and the theory of relativity and all these things and his scientific mind on a pedestal, you have to assume some of the following things. He did not have an actual source of gravity. He had models for how gravity behaves. He was a supporter of Lesage until Lesage got shot down, because there is no real mechanism that could be observed, and there was problems with, if these particles behave like this, then it should actually heat up the planetary bodies, and that's not what we're seeing. So even though he supported that kind of thinking, it was shot down by basically debunking it, because there was a problem in that model. He also supported something like growing Earth, because that's actually what it looks like it's doing, but there's no mechanism, so it got shut down. He hated the Big Bang. He thought it was wrong until you stacked up all these assumptions and the actual measurements, and then he had to eat his hat. So we have to assume that if we want to change things, we have to be proper scientific about it. We need to bring the proof and the arguments. And this happens when we start asking questions. What are you basing your assumptions on? And have you considered an alternative? Would something else, would a different model give us the same results?
Yeah, no, I agree with a lot of what you say. I will not go as far as to say as being able to bring down something means by necessity you have to be the one to elevate something else. I don't know if that's necessarily true. Being able to say, you know, going down this corridor, there's a pit with sharks, you know, and then you turn to me and say, well, you know, what other corridor do you want me to go down? You know, I'll turn to you and say, well, I don't know. You know, I mean, I think that it's laudable if, Jakob, as you say, if you are able to then say, look, this model is a better model, which is something that Johannes Kepler was able to do. You know, that's great, but it's not, I don't think it's necessary. I think it's just an added, you know, if you can do that, you're brilliant. I mean, you have, you know, you have hit the, you know, you've hit fist pump, done a great service for mankind. But I don't think it's absolutely necessary. I guess that's what I'm saying. I had another thought on, oh yes, one of the things I'd like to touch on, you know, Einstein, as best as I've read, Einstein was troubled by the vacuum, you know, the idea of that space was empty. And as time went by, you know, we've discovered that space, you know, is not empty. Space is space, you know, and, you know, you talk to any quantum mechanic individual who deals with space, they'll definitely tell you that space is something. Take any cubic centimeter of space in intergalactic space. You have virtual particles passing through there. You've got background radiation passing through, whatever that may be. You've got neutrinos passing through there. Space is a fabric, you know, and because of that, it leads to something very interesting. If space is a fabric, then work can be done because it has pressure. And the proof of that is the Casimir effect, which has now been shown to actually function. You can create mechanical energy from the Casimir effect. Now, what does that imply? It implies that Galileo's balls rolling down the ramps, yeah, just like Newton's thing, they work perfectly for the you know, for 99% of all functionality. But if you expand those ramps to 500 miles and you roll balls of different sizes down there, I'll guarantee you that the larger ball, the heavier ball, is going to arrive first because of the interference of space. To give you another example, take a spaceman, you know, in a spacesuit. You know, of course, you drop the hammer and the feather, and they fall perfectly and hit the moon at the same time. It works perfectly. It's great. But now take the spaceman and stick him 80,000 miles above the moon and drop in a pure, you know, without the interference in gravity of all the other stuff, and drop that feather and ball and hammer. So it was a hammer, and that feather is not going to reach the moon first because the interference of space go further out. Between, say you're dropping a hammer and a feather towards a galaxy, say from the distance of the diameter of that galaxy, that hammer is going to arrive first, again, because the interference of space. So our whole mindset that, you know, the laws of momentum and how things fall is basically wrong. And you can say, yeah, but it's such a small amount that it doesn't matter. But then again, you know, you look at Einstein pointing to Mercury and saying, hey, you noticed how Mercury, that little bit of error that's going on there, those errors are important. Those errors are really important. And this is important too. But I've not seen anybody discuss or take notice of this, and it kind of frustrates me. This isn't, again, this isn't a, I don't have a horse in this race. My interest is the sun, you know, and I'm very brutish, you know. I don't have the finesse of Jakob, and half of what he says I don't understand because I don't have the mental capacity to follow it. But I do.
But you have the problem back to. I like to go back to Democritus and the atomic theory. Basically, the whole concept is a thought experiment that is based on infinite division, right? If you just keep cutting a cake, right, or a log, at some point you will have a piece that's so small that your knife can't cut it. But it's the same when you're looking at when you're talking about things like the limitations of what we talk about in space, right? If you start saying, okay, what happens at the sub-Planck scale? What does the universe do down at scales smaller than elemental particles, or even smaller than, let's say, quarks?
This is where Chris needs a microphone.
Well, we don't really understand it for several reasons. First of all, how do you build a probe that can look at small things like that? What are you going to build that of? Right? So you have to do some sort of indirect measurement of what's going on down there. And you have had very, very interesting theoreticians talk about this, like talking about the Voronoi foam and how everything's like bubbling and foaming down on those scales. And then you start getting into the whole thing of, okay, if it's doing that and it's doing it at this frequency and this fast, and you can then see how, well, those vibrations are basically what feeds and sustains things like our electrons and leptons and all of that, right? So how much energy is then available in a cubic centimeter of this weird empty stuff? And then you start getting numbers that's just bonkers, right? This is when you start talking about things like the vacuum energy and and then you get into the whole ether problem again, because people then start calling this stuff ether, which is not entirely wrong, but it's also going to get all the wrong connotations.
It brings baggage along
right?
with it. Yeah.
Yeah. So the point is, let's assume, just for the sake of argument, that all of our models have been slightly off, right? If this stuff is really the most energy rich, energy dense stuff in the universe, that means that the stuff that we call matter and things that have gravity effects and all of these things are actually the less energy dense. That means that the balls are not billiard balls. The balls are more like bubbles. So all of our elemental particles are like empty bubbles with less energy density than the surrounding space. Then you get into starting to talk about things like, okay, if it does that, then how is all of this? Because then it becomes scaling up, and availability of energy is free. You can always borrow as much energy as you want for free from the universe, but it has to follow the rules of scaling, the scaling laws, right? So this brings into what is it that actually makes something like fusion work in a stable or semi-stable environment. But it's not stable because these things change and mature. And then you start having to actually look at how is the real noticeable cosmogenesis of the universe. And I personally believe that you would get further by talking to biologists than engineers. I think Teilhard Leschedeng is way closer, also a priest, by the way, to how the universe actually behaves. It seems to do many of the same things as we see in life.
Yeah, you know, I think it's a quote from Mark Twain. It says something, I'm paraphrasing, the events that occur on Earth are the same events that we see in the heavens. Let us not forget that lesson. But you know, I've always chafed at the division that we've created in sciences. You know, the think of the science as a pie that you split up into different cosmology, biology, electromagnetism, and all this, you know, stuff. And you know, as an artist, I sort of, because that's my training, I think of myself as being the cherry on top of the cake where all of these things draw together. So I don't suffer from that quote. What's that? An expert is someone who knows more and more about less and less. You know, I'm sort of you know, I think it's worthwhile to have generalists who are looking at the whole cake. And I've, as you say, Jakob, you know, we should maybe be looking more at, you know, what is happening in biology. And by the way, what is happening in biology at the moment is just way ahead of just about everything else. And their science with CRISPR-Cas9 and other aspects is rocketing ahead at the moment, where frankly, I think that in astronomy and cosmology, we're sort of like, you know, we're stuck. You know, we got this, you know, semi-religious Big Bang edifice, which ain't going nowhere. It's, you know, they're not allowing papers in that you know, that challenge and stuff. When CRISPR-Cas9 came along and you know, the publications, they were immediately accepted, and you know, the two gals, you know, won the Nobel Prize, and you know, full speed ahead, you know, whereas in cosmology, possibly to a large degree because there's so many intangibles and it's harder to prove anything, then, you know, it's more stuck. But right now, with the James Webb Telescope, looking at these galaxies in the dark ages, being there, you know, okay, let's maybe you can dispute it, but let's have the papers. Let's see them pass through peer review, and let's see them published. And then we'll take it from there. But that's tangible. This is first decent, tangible stuff we've had. I'm still waiting to see the telescope look at black holes. You know, so far that it's just been the general, black hole is the cloud, you know, so, oh, yeah, there's a black hole in the center. What I really want to do is I want to see the James Webb Telescope honing in on what presently is like, what, 9 pixels of size, from which scientists are trying to determine the configuration of what a black hole is. I think it's going to be very exciting when the James Webb Telescope starts really looking at that. I'm just praying that not a lot more little pings occur from particles in space hitting it, and certainly don't want one the size of a pea, which will affect hit it like a hand grenade. So, you know, I'm crossing my fingers that we're going to get more stuff, because this is tangible. This is stuff that you can really wrap your mind around. It's objectivity, I think, at its best. And I give you know, my cap, I doff my cap to the engineers and the visionaries who took the time and trouble to let us see the stuff that's out there in the galaxy. Thank you, guys.
Well, and this is what it all comes down to. We need to have engineers that can help us get access to actually seeing new things and basically visualizing and creating allegories and explanations and all of these things. But we do need the nutcases. We do need the crazy heretics. We do need the people that might have been doing too many drugs or start taking weird signals from his dreams to figure out, oh, wait a minute, maybe the biochemistry works like this instead, because you can have carbon in a hexagon shape and then suddenly modern medicine. But my point is, what I think is important for modern physics is to get out of the billiard ball way of thinking. We need to start looking at different types of allegories that are, I would like to see them use more things like what we know from biological systems, because they seem to be a lot better at explaining what is actually going on. recently, one of my favorite examples is that some scientists basically figured out that fungus can actually do random walk systems and optimizing paths. So basically the ant colony algorithm, they do that all by themselves, completely automatically, finds the best path, the fastest, the most efficient path through a medium, right? That's just the nature of a fungus. How does it do that? Well, we need massive computers
and how
stuff.
interesting that they mimic other phenomena, like lightning,
Exactly.
passing, or rivers, deltas that occur. I mean, to see nature repeat itself in the macro and microcosm is just amazing.
To get on to that, it's because there is some fundamental and very interesting and important underlying mathematics and physics at work here. It has to do with self-referential systems, so basically things like entanglement, and it has to do with minimal surfaces and what I would like to call minimal volumes. Efficiency is built in to the universe. It will always behave like this, but the math is quite complicated. It's almost, I would say, potentially inaccessible. I think we talked about this when I explained why in modern 3D modeling and computer universes, you cannot calculate everything that light waves will do when it has to bounce, reflect, and penetrate and deflect through and on media. It's just not possible, because you end up with an infinity problem and a non-stoppable problem. And that's why I'm almost going to be inclined to say we might actually need something like quantum computing, even though I don't actually think quantum computing will work. But we need a type of computing that can work and address this type of self-referential, non-stopping problem behavior. I wish I could actually resurrect Alan Turing, because I'm sure he might actually have some ideas on how we could do this. But right now we just don't have it. But when you look at the scaling of the universe, how it bifurcates, how it grows, how it contracts, and how it expands, it behaves like biological systems.
You mentioned talking about the biology and scales. Chris is telling me just here, by the way, that he still can't. He can't. His microphone, he can't get it to work. It's dropping out. Across the scales from the macrocosm to the microcosm, there are these themes that run through it, and I pay close attention to that. And one of the reasons that I have, again, one of my I'll eat my hat moments with black holes is, there is no instance that I can see in the other scales of nature pouring matter into a dumpster. And it's one of the things about black holes that I have a really hard problem with, is the idea that this phenomenon, let's get it straight, there is a black hole phenomenon. I don't think it's a black hole in the way they think it is. And I don't think that mass is being poured endlessly into these objects. One of the reasons I believe that is because I look at the accretion disk of plasmas. I think of the dynamo effect and know that plasmas, once the electrons and protons are organized, their force is much, much greater than any central force pre-black hole that could exist. But it basically, I think that we're going to look at these things and find that this is a functionality that the universe has made, that gravity is an important thing to the universe. And what it does is it likes to make more of it. And the way it makes more of it is not just by clumping a bunch of matter together, but it has a way of creating the illusion, not the illusion, creating more gravity without a corresponding quantity of mass. And maybe that's something I'd like to talk about next week some more with Jakob. Jakob, I thought this time we would we would
End a
keep
little
it
bit earlier.
under
I would just like
2
to say
hours
that
and 23 minutes. So let's give
would.
it
Can I just
a
finish
5 more
on a
minutes.
note on a comment to the black holes, right? Because I think it's important that if you work from the assumption of a gravitic model that magically creates pull based on increasing density of matter inside a stellar body, then you get black hole models that we have now. But if you flip this on its head, and if you consider maybe Lesage was actually onto something more real, with actually coming from the ambient outside of matter, that means that the gravity is not something that's inside the sun that's pulling it, it's something outside that's pushing it. This is important because why would you then have something like the black hole effect? Well, you would have that from the same effect as a lens. It's basically an event or a location in space where all the surrounding matter is causing an effect at that point without any glowing body. This is back with, if I could magically remove all the photosphere and the entire matter of the sun, there would potentially still be an actual black hole at the center. The singularity nature is emergent from gravity being a pushing force. It seems like radiation, but of course it's not. It's more like buoyancy and osmotic pressure, if anything. If you want to compare it to anything, think of osmosis and think of empty space being like a non-Newtonian fluid. If you push on it, it pushes back. If you pull on it, it pulls back. It's elastic, right? And when that is surrounding matter, it will always try to push on it based on the size and the type of material available. But it's also going to be pushing from the inside. But at the center, you have this complete, almost like a pure vacuum. This is a black hole, but that is an event based on a push gravity concentrational force at the center. So it's the galaxy and the galaxy's volume that creates the black hole at the center of the galaxy and at the center of the Earth and at the center.
That's really interesting. Yeah.
So it's an event. It's a bit like when you create a vortex, it's empty, but all the material is what's basically around it, right? So it's about creating new aspects and new models, thinking about these things a little bit upside down and revisiting some of the old theories, because just like the atomic theory, sometimes we need to revisit old theories because they actually can be proven now.
Right. I mean, like you say with ether, you and I roll our eyes when we hear it, but we both acknowledge, that space is not empty anymore. And Einstein was kind of like glad to hear that. From what I've read, he went through an age where space was empty. When he wrote his most important work, it was an era where, Michelson Morley had basically removed the concept of the ether. And probably so, because the ether was just, a mysterious, magical stuff that couldn't be verified. Well, now space can be verified, and it isn't empty. And in fact, I'm pleased to see that there are other people who say, if you had an area of space that if you removed space, well, then you remove time. I just saw an article about that a week ago, and I'm just going, yes.
If you think about it, right? If you consider what the nature of the vacuum is, how dense it is, how energy dense it is, then something moving through it is a bit. It doesn't have any lag. It's just too solid. It's a bit like, again, I like to use the analog of sound. If you consider sound moving through an infinitely dense matter, then it would move through it instantly. the denser the matter is, the faster things move through it. So the propagation through space is basically what is telling you exactly how dense empty space is. You can measure that by actually measuring the speed of light. If you can measure the speed of light, you know how dense it is.
We're almost touching on entanglement at that point. The instantaneous action from in one part of the universe to another is now pretty much accepted in physics, which I just found astounding, and something that we'll leave until next week, because I think we should draw the time closed for now. But Jakob, I just love talking with you, man. Like, yeah, you're the sort of like foil that I really enjoy, and I so missed Chris not being with us today, and hope that he gets his computer up and running properly for next week. I'll see if I can touch base with him and help him with that. He did mention a piece that we were talking about called the quantum foam gravitational waves by Reginald Cahill, and we didn't get a chance to talk about that, so I'm hoping that next week we will. So I'm gonna keep you on for a little while, Jakob. I'm gonna stop our recording and hope to see you all somewhere out there in the new ether.